We are embarking on the journey of logarithms. So, sorry, this is a one-way dead-end road. So, today we need to review exponents. Yes. We're not actually doing logarithms today, we're just doing exponents. Hey, I don't negotiate with terrorists. So, a certain forest covers an area of 2,600 kilometers squared. Suppose that each year this area decreases by 6.25%. What will the area be after 7 years? So, linear equations. Y equals mx plus b. What does this number tell me? Y-intercept. What is this? Your slope. Okay. I like to build exponential equations using the same variables. I don't know anybody else that does it that way. But for exponential equations, I like to write y equals b times m to the x. And this is the y-intercept. And this is the rate of change, but it's not linear. It's exponential. So, how do you increase a number by 10%? Multiply by 110% or 1.1. Everybody understand how to do that? You can do it the slow way. Take your number, times it by 10%, add that to the original value. But it turns out if you multiply by 1.1, you do it all in one step. How do you drop, in this case, 6.25%? So you take 100% and you subtract 6.25%, and I get 93.75%. As a decimal, that is 0.9375. Does everybody understand that? Multiplying by 0.9375 is the equivalent of subtracting 6.25%. And one way to think about it is if you take everything you have and you throw away 6.25%, how much do you keep? 93.75%. So, let's plug this into our exponential formula. This is the y-intercept. Right now, the forest has 2,600 kilometers squared. And we are changing that by 0.9375 to the x. And this equation wants to know what happens 7 years from now. So we're going to plug 7 right there. Calculator. So 2,600 times 0.9375 raised to the 7th. After 7 years, we'll only have 1,654 kilometers squared. Okay. What if the forest grows? What if the forest is growing 12% each year? We take that same 2,600, we times it by 1.12 to the 7th, and then we figure out how big it would be at the end of that 7-year cycle. So 2,600 times 1.12 to the 7th, and I get 5,747. Everybody understand that? Okay. Oh, I know what's going on. I need to push this button. There. That will work. All right, number 2. $2,000 is invested at 3.5%. How many years will it take to get to $3,000? So y equals We start with 2,000. How do we increase 3.5%? 1.035. And we're going to leave it in for an unknown amount of time. Where does the 3,000 go? Goes right here. 3,000. Now, this is trickier than it looks. What do I need to do to solve this? Can I multiply the 2,000 into there? No. Order of operations says exponent comes before multiplication, so I cannot multiply the 2,000 in. So instead, I divide by 2,000, and I get 1.5 is equal to 1.035 to the x. How do I get the x out of the exponent? You can square root it by the exponent. So root x, xth root, and I get the xth root of 1.5 is equal to 1.035. Now how do I get the x out of the root? You raise it to the x. But I was just there. So that didn't work. And this actually is not algebraically sound, because in order to take a root, we have to know what the number is. Because square roots and third roots act differently. Some of them create imaginary numbers and some of them don't. And fractional roots, or decimal roots, are even more complicated. So it turns out that this step, even though it looks okay, it's not actually legal. So that didn't work. So it turns out none of this stuff had any value. Okay. What do I do? I could graph it, yes. But there has to be an algebraic way to do it. We could guess and check, and that's kind of what we're going to do today. But there are algebra tools that you don't have yet. They're called logarithms. Logarithms were invented to solve this problem, because the best we can do at the moment is to guess. And watch how much fun it is. Okay, then close your eyes if you don't want to see this. So 2,000 times 1.035 raised to the, anybody have a guess? 6. Is that big enough? No. So now I have to do second, enter, then I go over here, and I put in, let's say, a 9. Not big enough. So I do this again, and I say 20. Too big. That's a pain. Okay? Here's a better way to do it. I gotta turn my plot off. But I'm gonna type in 2,000 times 1.035 raised to the x. Then I can graph it. Oh, that's not what I wanted. I wanted this. I don't see anything. Why don't I see anything? Starts at 2,000 on the y. Turns out, I don't really care if I see the graph or not. I can still plug numbers in. If you push trace, then you can just start plugging in numbers. 2, 3, 4, 8, 9, 10. And when I try to plug in 11, I get error. How come? 11 is not an x value that appears on the screen. So in order to do these guesses, you got to change your window to fit your needs. So I'll put my x max at 20. Now I can do trace. I can type in 11, 12. 12's too big. So let's do 11.5. 11.6, 11.7, 11.8. Anybody else sick of this? 8's too much. 11.75. Horrible. Okay? But I'm going to be nice to you. You don't have to get the decimal. What does it say? Find the smallest possible whole number answer. So keep guessing until you break it, and then go back to the one before it. Okay? Now, is there a faster way to do the guesses? Yes. You go to the table. So, second table, and now I just scroll down, and I pick the number that is as close to 3,000 as I can get without going over. So in this case, the answer is going to be 11. Closest without going over. Yes. No, I'm not sure. Let's try it. Maybe I'm wrong. So if I try 11, oh, maybe it's, you do go over. Oh, okay. So as soon as you go over, that's the one you want. Thanks for pointing that out. It's not like my pride is hurt or anything. Okay, do you guys understand that? So really there's no guessing involved. The old way to do it was to guess. And after mathematicians had to guess, they didn't have calculators. After they guessed for a while, they said there's got to be some better way to do it. Well, it turns out they had to invent new mathematics to solve it. And the new way to do it is essentially guessing as well. But it's guessing in a different format. And anyway, we'll get to that later. Okay. Number 3. So suppose that the dollar value of a car is given by this equation. How much was the car worth initially? $29,900. Does the function represent growth or decay? Is the value going up or down? Up. How do you tell? M is bigger than 1. How much bigger than 1? 25%. Okay. Number 4. There was a sample of 900 milligrams of radioactive substance to start a study. Since then, the sample has decayed by 4.5% each year. Write an exponential function representing this. Oh, this one's easy. So it's going to be y equals 900. Are we going up or down? Down. How do we go down 4.5%? So 100 minus 4.5 is 0.955 to the x. Oh, t. T. Okay. Can you handle that? Whether you can or not, I guess you got to try. Get to work.